If you have a 6-sided die, your chances of rolling a 2 is 1 in 6. With a 100-sided die, the chance of rolling a 2 becomes 1 in 100. If you use a die with 1 billion sides, your chances are literally 1 in 1 billion. But what happens if you have a die with an infinite number of sides? The answer is an infinitesimal, a number that makes calculus work and calculating area possible. An infinitesimal is a number that is infinitely close to 0, in other words, 1 over infinity. Over the history of mathematics, infinitesimals have proven incredibly useful, despite being about as controversial as math gets, and never really sitting right with mathematicians. Using infinitesimals, a whole new way of thinking about math, non-standard analysis, has been introduced, allowing for a more intuitive approach to complex mathematics and shorter and simpler proofs. Imagine a number line of all real numbers, called n. Where does infinity fall on this line? The answer is that it does not. Instead, infinite numbers lie on a separate number line, which we will call n prime, on which the central value is k. Just like on n, numbers on n prime have properties. They can be even or odd, they can be squares, and they can be primes. And, similarly to no matter how much you add to a number on n, you will never reach an infinite number, no matter how much you subtract from a number on n prime, you will never reach a finite number. All the operations that work on numbers on n also work on numbers on n prime. You can add and subtract, creating values like k plus 1 and k minus 1. You can take opposites, creating a whole new number line, this one centered on negative k. And you can take reciprocals, creating values like 1 over k, a number which is closer to 0 than any real number. You can also take reciprocals of the other numbers on n prime. Some, like 1 over 2k, are closer to 0 than 1 over k, while others, like 2 over k, are farther. But all of these numbers are still closer to 0 than every number that is on n. This creates something called the infinitesimal monad, an infinite group of infinitely small values. This is only one way of defining infinitesimals, but no matter how you arrive at them, infinitesimals have the same properties. Infinitesimals are closer to 0 than any real number, and they remain infinitesimals if multiplied by real positive values. Although most mathematicians agree that infinitesimals should not be used in formal proofs, they can still be incredibly useful, especially when it comes to area formulas. To introduce ourselves to this idea, we can find the area of a circle using infinitesimals. Imagine a circle with radius r. To find the area, we can split C into an infinite number of sectors, each with an infinitesimal arc length. Because the arcs of the sectors are infinitesimally small, they approximate straight lines. Because of this, we can rearrange the sectors into a rectangle, with the arcs making up the longer sides. The shorter sides of this rectangle measure r, the radius of C. The length of all of the arcs of the sectors, when summed, is equal to the circumference, 2 pi r. Because only half of the arcs make up each of the longer sides of the rectangle, each of the longer sides only measures pi r. The area of the rectangle, and, by extension c, is r times pi r, or pi r squared. This is a simple way to explain why the formula to find the area of a circle is a equals pi r squared. A much more common use of infinitesimals is in finding the area under a curve, one of the main topics of calculus. We can use infinitesimals to find the area under a curve by fitting an infinite number of infinitely thin rectangles under the curve. Because the tops of the rectangles are infinitesimally small, the sections of the curve that they touch approximate straight lines, and the curve is always in contact with a rectangle. The area under the curve is equal to the sum of the areas of these rectangles, the heights of which can be found using the rate of change derivative of the curve. This is the method that Leibniz, one of the inventors of calculus, used to prove his findings. Since then, mathematicians have discovered limits, a way to perform these calculations by only using real numbers. Many mathematicians disagree with the concept that an infinitesimal segment of a curved edge can be treated as a straight line, and believe that explanations like the two in the previous section are inherently flawed. Most mathematicians agree that, as infinitesimals are not real numbers, they should not be used in proofs. To get around this, Abraham Robinson created non-standard analysis, a way of doing mathematics in a system that includes some non-real numbers in the 1960s. In this system of analysis, Robinson created the hyperreal number line, which includes all real numbers as well as the hyperreal numbers, numbers that are the result of sequences of real numbers, that is, infinite and infinitesimal numbers. The hyperreal number line is the system that was explained in the defining infinitesimal section, and numbers like k, negative k, and 1 over k are examples of hyperreal numbers. If hyperreals are allowed to be used, complex proofs become more intuitive and shorter, so many supporters of non-standard analysis choose to use hyperreals like infinitesimals.